okay? Now, let's look at them together. So first two question is related to expectation, okay? Remember, for the potential outcome framework, the whole sort of like key tool of analyzing causal effect is via expectation and conditional expectation. So the first statement here is the expectation of a random variable y is the weighted average of all possible outcomes that it could take, okay, where each outcome is weighted by its probability. So essentially we're saying that expectation is just some probability weighted average of all the possible values that y can take, okay? That should be covered in advanced stats. This is a true statement, okay? Think about it. What actually is expectation? Expectation is just a long-run average. It's the average value of a random variable in the population. And think about it, how you actually calculate the sample mean. Okay, so in the calculation of the sample mean, we are actually computing the sample average of y as that's 1 over n. So we're dividing the total sum of all the values of y in the sample by n. Okay, and effectively, this is a weighted average y. If you look at it, okay, if you move the 1 over n inside, essentially, you're weighting every single value of y in your sample by 1 over n. So it's an equally weighted average. It's just that the same weight applies to every single person, okay? But in general, like, if we think of it in a slightly different way, instead of saying that y is the value of a single person, we think about it in terms of the y of the possible values that it can take. You know, some person, they can share the same value of y, where y actually happens to take the value three times, okay? So suppose y can only take 3 values, y1, which is 3, y2, let's say it's 0, okay? And y3, let's say it's 1. And we might observe like y1 being 3, let's say 10 times in the population, and y2 being 0, let's say 5 times in the population, and y3 being 1 5 times in the population, okay? So basically it means that in total, in the population, we have 20 observations where y1 happens to be equal to 3 with a probability 10 over 20, that's a half, okay? Whereas y2 happens to be equal to 0 with probability 5 over 20, that is just 0.25. And similarly, for the value that y3 can be 1, okay? Then in this case, we find the average value of y by simply weighting each possible values that it could take, okay? This little y represents all possible values that the uppercase y, the random variable itself, can take, okay? So uppercase is a random variable, lowercase y is a real number, okay? It's just a constant. Then we weight 3 by 0.5, and it can be 0 with probably 0.25, and it can be 1 with probably 0.25, okay? Then we have 1.5 plus 0.25, which gives us 1.75. So the average value of y in the population, given that we have only 20 observations in the population, is just 1.75. Okay, so remember, expectation is the weighted average. Okay, nothing special about expectation. In the end of the day, it's just tell us on average what is the value of the y that is most likely to happen. So this is a true statement. Now the next one. We have that the expected value of a random variable y can be computed as the weighted average of its conditional expectation. Okay, so suppose given y and some x, the overall expectation of y can be recovered by computing the weighted average of all these conditional expectations, okay, with the weights given by the respective probabilities of these conditional events. So here, the probability is given by when x is equal to the lowercase x. Just think of x as d, a binary variable, okay? It's either 0 or 1. So this is, again, a true statement, okay? Think about it. Imagine x stands for the dummy variable gender. The overall grade of this class can be think of as the average for girls and the average for boys. Okay? You're just reweighting the average of girls and the average of boys by their respective proportion in the class. Then similarly, think of girls as being treated and boys being untreated. Then the overall grade of this class is simply the weighted average of those who are treated and those who are not treated, okay? So this is really by the property of lie. Okay, remember that the conditional expectation, we have very useful property for it. If we take the expectation of the conditional expectation of y given something, it will give us back the overall expectation of y. That's the lie. Okay? And remember, the conditional expectation, which we talk about a lot of times, the randomness comes from the d, the variable that we're conditioning on. Okay? So this conditional expectation can take two values, given d is either 1 or 0. So the overall expectation is then the value of the expectation given that d is 0 multiplied by the probability that d being 0 plus that the expected value of y being given that d is 1 multiplied by the probability that y is 1. Okay, the d being 1. So this is something you should keep in mind. Another way to think about it is just think of it as this is just another random variable z, okay? This is all the possible values that z can take, and this is the probability that the uppercase z is equal to the lowercase z, okay? So this is how we link conditional expectation with expectation via lie. Now, the next one, exclusively related to what we covered on Monday. So, treatment effect depends on actual treatment status. Can this be a correct statement? Okay, quite a balanced vote. So, this is a false statement. The treatment effect does not depend on the actual treatment status. Okay, remember how the treatment effect was defined. The treatment effect is defined to be the difference between the two potential outcomes. Okay, what would have happened to you if you were treated compared to what would have happened to you if you were not treated? It's the actual outcome that you observe that is related to the treatment status. Okay, the treatment status is related to the actual outcome observed, but that is just one dimension of the treatment effect. Okay, what constitutes an effect is the change that we have observed given a change in the status. Okay, so to compute an effect, we need two outcomes, but the actual treatment status only relates to one outcome. Okay, so and it's the one of the potential outcome that's actually realized. Okay, so knowing the actual treatment status doesn't help us to derive the treatment effect. The treatment effect only relates to what would have happened if your treatment status is changed, okay, going from 0 to 1 or from 1 to 0. So keep this in mind. Now, another way to think about it is that if you think of the actual actual outcome as if the treatment effect, then essentially, inherently, you're comparing the before and after you. But the treatment effect is about comparing the same you in the same state. Imagine at the same point in time, there are two universes, okay? The two universes only differs in terms of the treatment status. In one universe, you're not treated. In the other universe, everything else is the same, but that you are treated, okay? It's about comparing that, not comparing before and after. So the actual treatment status doesn't tell us anything about the treatment effect itself. So this is a false statement. The last one. The fundamental problem of causal inference is we can never observe the full set of potential outcomes. This should be something quite simple. Okay, this is true. Treatment effect involves comparison of two potential outcomes. But in practice, we only observe one, depending on your treatment status. Okay, remember where we stopped on Monday. Given someone is treated, okay, DI being 1, we only observe the potential outcome with the superscript, the value of the superscript that matches your treatment status. So for DI being 1, we only observe the potential outcome Y1. Likewise, for someone who is not treated, your value D is 0. So we only observe the potential outcome Y0. We never observe Y1 for those who are not treated, and we never observe Y0 for those who are treated. Okay, what makes causal inference hard is because of these missing cells. If we know the value of these cells, then causal inference would just be so simple. Okay, so the fundamental problem is because we can't observe the full set of the data set that theoretically we want to observe, and thereby making the calculation of the treatment effect hard, and we need to find some solutions to help us to rectify the missing data issue, okay? And remember, the ATT is easier to identify because it only involves one dimension of the missing data, whereas the ATE, the average treatment effect in the population, okay, we can see that we can't compute either the mean outcome for everyone that is treated or the mean outcome for everyone that is not treated, because both columns involve missing data when we need to compute the ATE. So it's much harder to identify the average treatment effect in the population than that for the treated subgroup, okay? So this is where we stop on Monday. Now, to make the problem of causal inference a bit more specific, so remember the ATT relies on the unobserved counterfactual, okay? So the ATT is the difference between the outcome in the treatment state and the control state for those who are treated, and we take the average. So these two conditional expectations, we only observe the first one, where the superscript of Y matches the value of D, but we never observe the second one in real life, okay? We never observe Y not given someone is treated. Then we can't compute ATT directly, but we do observe something that looks similar to the counterfactual, okay? While we cannot observe the outcome for the treatment group had they not been treated, we do observe the outcome for the control group if they are not treated, okay? So this is the observed outcome for the control group because the superscript Y matches the value of D. Then essentially, the observed difference between groups is just the mean outcome of those who are treated, subtracting those who are not treated. Oh, sorry, it's me. It's my alarm. Sorry about that. Okay. So this is the observed difference between groups. And we can see that comparing to ATT, it's the second term that is different. Okay? We are subtracting the observed outcome of the treatment group by different terms. Then that will imply, in general, the observed difference between group would not equal to the ATT. Okay? So imagine this is the observed difference between group. And if we simply subtract and add the counterfactual outcome for the treated, okay, then we'll get the ATT and also a term which is the difference between the mean outcome for the treatment group and the control group in the control state. Okay? So this equation is very important. This is called a fundamental equation of causal inference, which essentially highlights why causal inference is hard, because of the selection bias term. And essentially, the selection bias term involves something that we never observe in practice. So the observed difference is the sum of the ATT, the average treatment effect on the treated, plus the selection bias. And therefore, you should never naively interpret the observed difference between groups as the causal effect. Okay? You should always think about the potential of having selection bias. So what does that imply for our data set? So we know that given this table, because these values are missing, so we can't compute the overall average for the outcome in the treatment state. And because the Y naught is not observed for the treated, therefore we cannot compute the overall average of the control state outcome. And similarly, because precisely we never observed the outcome had the treated been not treated, we can't compute one of the conditional average for those who are treated. Okay. Then given missing, we can't compute the difference. And with one missing value, we can't compute the difference either. But we know that we have the observed outcome for the treatment group, and we also have some observed outcome for the control group. Okay? So if we take the observed outcome for the control group and compute the average, which is just 4/3, that gives you 1.33. Okay? Then we can use this to compute the observed difference between groups. So the observed difference is just 2.5 minus 1.33. Okay? And that is the 1.17. But recall previously we've already seen that the true values of the ATE is actually 1.8, and the true value of the ATT is actually 1.5. So generally, the observed difference between groups will not be the same as the treatment effects that we want to identify. And this is really because of the selection bias. Okay? So again, selection bias is the difference between the mean outcome between the two groups in the control state. Okay, the selection bias refers to the outcome in the control state. So we compare the actual outcome of those in the control group with the counterfactual outcome in the treatment group. It's because of the first term that makes this bias unobservable. Okay? And typically, selection bias is different from zero in most observational studies. So for example, think about the tobacco cessation program we discussed on Monday. So the participants, those who self-select into the program, they might inherently be more likely to quit because they are more determined to quit. then in the absence of the program, those who are in the treatment group are more likely to quit smoking. Okay, so the control state outcome for the treatment group is higher than that for the control group, because the treated are just inherently more determined to quit. Okay, so selection bias is different from zero in most cases. And what we really want is to make the selection bias zero. Okay, then because without the selection bias, the observed difference between groups will recover the treatment effect that we are interested in, the average treatment effect on the treated. Okay, you can think of this as, with no selection bias, basically these differences are zero. Then we can use the observed outcome for the control group as a reliable prediction, approximation, estimation of what would have happened to the treatment group in the control state. Okay? So basically what we're doing for the rest of the week is about exploring some causal assumptions that allow us to potentially get rid of the selection bias term, so that we can make the observed difference between groups to be equal to ATT in value. Okay? So before we look at the slides for today, so just to show you how what we've done in semester one actually connects to what we're doing right now. So the population linear regression model, or even the linear causal model, in the framework that we discussed in semester one, is related to the observed outcome. Okay? The potential outcome concept is related to the potential outcome framework. So the population linear regression model, where we regress the observed Y on the treatment status D, and here the D, the dummy variable, so it's binary. So the conditional expectation of any random variable given a binary variable is always linear. Check the notes for the derivation details. It's actually very simple. Okay? And then remember that the conditional expectation of Y given D, given some variable, is the best nonlinear prediction for Y using D. But since this best nonlinear predictor actually takes a linear form, then it must also be the best linear predictor. Okay? But we know that the best linear predictor is essentially given by the population linear regression function. Then that implies the conditional expectation of Y given D must also equal to beta naught plus beta 1 times the treatment status. Then what does this imply? Okay, if you set D being 0, so the second term disappears, then the conditional expectation of Y given that you're in a control group is just beta naught. Okay, whereas if you switch D back to being 1, then you just replace 1. So the conditional expectation of the observed outcome, conditioning you are in the treatment group, is just simply the sum of the two constants. But then that implies we can actually connect this with what we're doing in potential outcome framework. Okay? If you take the difference between these two conditional expectations, that is essentially the observed difference between groups. Okay? And using the fundamental equation of causal inference, we know that this observed difference is simply the ATT plus the selection bias. So that implies when selection bias is 0, which is akin to exogeneity, the beta 1 will be mathematically equal to the causal effect, which is the ATT. Okay? Whereas in the case when it's different from 0, that it's akin to the problem of endogeneity, then the beta 1 will not help us identify the treatment effect. Okay? So this is how the population linear regression model that we've seen in semester 1 actually relates to the potential outcomes framework. And we'll see that it's actually very useful even within the potential outcome context. So this is the rest of the slides for Monday. Now, today. So let's look a little bit more into the details of what does no selection bias mean. So essentially, we want these two condition expectations to be the same. The mean outcome in the control state is the same across group. Now, saying this might sound something very simple, but actually the condition to ensure no selection bias is very subtle. No selection bias does not require balanced characteristics in both groups. Okay? We don't require that if we see, people that are more healthy in the treatment group, they should be more healthy in the control group as well. Okay? But it's that the effect of the characteristics on the outcome must be balanced. Okay? So it's not about the distribution of the characteristic itself, but it's about the effect of the characteristics in the control state. So coming back to the tobacco cessation program example, and suppose for simplicity, apart from the program itself, there are only two determinants of quitting. One is how determined you are, and one is your health status. Okay, so the more determined you are, the more likely you'll quit. The more healthy you are, the more likely you'll quit as well, because maybe you're just more health conscious. So suppose that the group characteristics are as follows. Okay, the treatment group, they are more determined, but they are less healthy. Whereas the control group, they are less determined, but they are more healthy. So we can see that the characteristics are not balanced across group. The distribution is different. But even though that the distribution is different, their influence on the outcome in the control state can be the same. Okay? Think about it, being more determined offsets being less healthy. Okay? And for the control group, being more healthy offsets being less determined. So we can reach a balance between the two groups in terms of the effects, such that the mean outcome is the same, absence of the treatment. Of course, ideally, we really want that the two groups to have similar characteristics. Okay? And then that just sort of make the world simple. That this inherently balances the outcome, even in the treatment state. However, this is more than what is required to achieve no selection bias, and typically, a similar characteristic distribution across group can only be achieved via randomization, which can only happen in control experiment. But in observational studies, it's really hard to achieve randomization. So typically, we won't be able to see similar characteristics across groups, but at the best, we hope that we'll be able to see similar effects of the characteristics across groups. And another concept that is kind of related to selection bias, but they're completely different. So we have selection bias and selection on returns. So selection on returns is just another name to refer to the situation where the average treatment effect on the treated is different from the average treatment effect in the population. Now, the selection on return is not a bias, nothing wrong with it. That is just because of heterogeneity, okay? Because the treatment has different effects for every single individual in the population. Therefore, when we're considering the average of different groups, then in general, these averages will tend to be different. Nothing wrong with that. Now, no selection bias does not imply no selection on returns. Okay, so no selection bias does not make ATT to be the same as the ATE. Why? So suppose we see a different data set. So here we have the Y being the decision to quit. Okay, so Y is 1 if one end up quitted, and Y is 0 if someone end up not quitted. So we can see that again, we only observe the treated state outcome for those who are in the treatment group, and we only observe the control state outcome for those who are in the control group. So this would make, because of these missing values, we can never compute the overall averages, okay? And also because of this missing value, we can't compute the average for the treatment group had they not been treated. But if we happen to have no selection bias, then that will help us re-identify one term, okay? So think of now, we also do some computation for those who are in the control group. Sorry, I think there's a typo here. This should be 0. And also on the slide. So given that someone is in the control group, we never observe the outcome had they been treated. So this cell is missing. But we do observe the outcome had they not been treated. So the control state outcome, which is just 1 divided by 3, that gives us a third, okay? Then given there's no selection bias, we know that these two should be equal, okay? The control state outcome should be the same for those who are in the treatment and the control group. So it makes this cell equals to 1/3 if there's no selection bias. Then given we have the value 1 for the treatment state, and we have the value 1/3 for the control state for those who are in the treatment group, then we're able to compute the effect, which is just the difference between these two. That gives you 2/3. Okay? Now, ATT can be identified in this case if no selection bias. However, we can't recover ATE. Why? So the overall average for the control state is essentially the weighted average of the treated and the untreated in a control state. So this value can be computed if there's no selection bias, because it's simply 1/3 for those who are in the treatment group, okay, weighted by the proportion of those who are treated, that is just 2/5, and then plus 1/3, which is the outcome for those who are not treated, again weighted by their proportions, which is 3/5, okay, but that is just simply 1/3, okay. The weighted average of the same number is just the number itself, 1/3. So we can identify this, that's good, okay. We know this, that's good. We know the outcome in the control state for the untreated, but we don't observe the outcome for the control group in the treatment state. This is not observed, which makes ATC unobserved. And similarly, that would make the overall average for the treated state unobserved, missing. Okay, this is missing because this is inherently missing for the control group. And therefore, although we can identify this cell, if there is no selection bias, we will not be able to compute the difference because there is still one value missing. So, okay, no selection bias does not imply no selection returns because we can't compute the ATE. Then we never know whether ATT is equal to ATE or not. So the key here is really because the no selection bias is only related to the control state. Remember, it's about comparing the mean outcome across group in the control state. If they are the same, no selection bias. But that does not tell us anything about the treated state. Okay? So it does not ensure we can recover ATC, the average treatment effect for the control. And therefore, we can't recover the ATE because the ATE is simply the weighted average of ATC and the ATT. So this is how we can sort of visualize this. No selection bias does not imply no selection on returns using a table. So how do we conceptualize this? Again, using the tobacco cessation program example. So same setup as before, those in the treatment group, they are more determined but less healthy. Those in the control group, they are less determined and more healthy. And suppose we achieve no selection bias, so the effects of the characteristics balanced in the control state. Now, we can still have the ATT being different from ATE because the treated state outcome are different. How? Imagine there's different interaction effects between the treatment and the characteristics. Okay? Suppose the program benefits those who are more determined significantly more than those who are more healthy. Okay? Then that would imply the program would benefit the group who are more determined more. So the ATT, the average outcome, the average effect in the treated state for the treatment group will be greater than that for the control group, okay? Because the effect of the treatment is greater for the characteristics of the treatment group than that for the control group. So even if we have no selection bias, we do have selection on returns because the outcomes in the treated state is different. So in order to achieve no selection on returns, we need some extra conditions. The first one is either we have homogeneity. Okay, so the treatment effect is the same for everyone in the population. And then that will naturally imply the ATC, the ATT, the AT, they are all same. The treatment effect for any subgroup would be the same. Or it could be that we have a balanced interaction effect. Okay, suppose the interaction effect is not like this. Not that the program benefits more for the more determined than for the more healthy. Suppose that the program benefits the more determined more than the more healthy one, but this effect decreases as one becomes more healthy. Okay, then in the end we'll be able to offset these interactions such that we achieve an identical outcome in the treated state, given no selection bias. Or the ideal case would be that we have equally distributed characteristics. Then regardless of their treatment effect or not, doesn't matter because the characteristics will be just the same across group. Even if there's treatment effect, we'll still get identical outcomes in the treatment and the control state. So the bottom line is no selection bias does not imply no selection on returns. They are different. Selection on returns concerns two states. Selection bias concerns only one state, okay? So they're different. So what we're going to do is we want to get rid of the selection bias term. We want to identify the ATT. And in order to get rid of the selection bias term, essentially, we want to make the mean outcome in a control state to be the same across group. Then how do we actually achieve that? We need some comparability between those who are treated compared to those who are not treated. So in order to get rid of selection bias, we need to understand how some individual become treated and how some individual becomes not treated, the assignment mechanism. Okay, so how the units are selected for treatment. So today we're going to talk about random assignment, hopefully in the last 5 minutes. And then next week, we'll talk about selection on observables, depending on observed characteristics. The week 11, we'll talk about selection on unobservables, so depending on unobserved characteristics. So we typically identify the treatment effect through restricting the treatment assignment in some way. So we've already kind of talked about randomization. So the random treatment assignment basically ensures everyone equally likely to be assigned to the treatment or the control group. This is the perfect scenario because it just balances the control and treatment group concerning their characteristics and their effects. Okay? So basically, if we see more people with brown eyes in the control group, let's say we still see 80% of people being brown eyes in the control group, we'll see 80% of people being brown eyes in the treatment group. And if we see more males in the control group, randomization ensures that we also see more males in the treatment group. Okay? If the average height of the treatment group is 1.8 meters, the average height of the control group will also be 1.8 meters on average. Okay? So randomization ensures that the characteristics, regardless of it's observable or unobservable, to be identically distributed across the groups, that inherently they are comparable. Okay? The potential outcome, regardless of in the control or the treatment state, will be the same across group because their characteristics are exactly the same on average. Then this would imply mathematically, okay, if you think about it, the potential outcome being the same regardless of you're treated or not treated, then essentially it just doesn't depend on the treatment status. So the implication of random assignment is that potential outcomes are independent of treatment status. It's the Y1, Y0 being independent of D. Basically, that means, okay, any individual, regardless of how good or how bad their potential outcome is, that wouldn't make them more likely to be treated or to be not treated. And one thing you have to keep in mind is that the treatment assignment does influence the actual outcome. Okay? The treatment assignment is dependent on the actual outcome, but the dependence is between the assignment and potential outcomes. Okay? So this is the randomization. Then basically, given independence, it's perfect. Okay? Remember from our time series analysis, independence implies conditional mean independence. If treatment status is independent of the potential outcome, knowing the treatment status will not help us improve our prediction for the potential outcomes. Okay? So the conditional expectation of Y1 or Y0 given D would just equal to the unconditional one, because knowing extra information does not help us improve our prediction other than using the average value of the variable itself. Then this naturally eliminates selection bias. Okay? Remember, the selection bias are the differences between the two conditional outcomes in the control state. Given independence, these two conditional expectations will become the unconditional one. But this is just the expectation of Y0 subtracting the expectation of Y0, which is naturally 0. Okay? So this is really because the observed and unobserved characteristics are balanced. They're equal in both groups. So selection bias. This is the mean outcome in the control state for those who are treated minus the mean outcome in the control state had they not been treated. Given independence, we must have that this is equal to the unconditional expectation, and similarly, this is equal to the unconditional expectation. Sorry. Okay. So given that they are the same, when you take their difference, that is just 0. Okay, so this is how selection bias becomes 0. Then given that selection bias is 0, the observed difference between group will just be the same as the ATT. Okay, then we can give the observed difference a causal interpretation. And on top of that, the ATT will be the same as ATE. Remember, one condition to achieve no selection on returns is that the characteristics are balanced across group. Randomization ensures characteristics being balanced across group, so we'll have ATT the same as ATE. Therefore, random assignment ensures that the observed difference between groups gives us the value of ATT, which is the same as the value of ATE. Okay, so I'm going to stop here today. I think that that's already a lot. So I'll wrap up on the next 2 slides on next Monday, and we'll talk about the implications. The feedback for midterm will be available at 5 today. I mean, on average, you did very well. I haven't released the grades yet, but the raw average was 67.32. Okay, the overall average, which once we take into account the bonus, becomes 86.66. Okay, because we need to cap at 100. Make sure you go through the feedback. Okay, the 2 questions that has the lowest performance were actually one of those that's supposed to be more simple. So question 6 and question 3, make sure you go through the feedback. So have a good weekend, and I'll see you on next Monday. The lecture notes will be released later today. Okay.